Recording. So welcome everyone to our Big Data AI Hub seminar series. Today, the session is on quantum computing and its application in finance. As usual, we will be recording the session and the recordings will be available on the website. However, if you are a U of T student and would like co-curricular credit, or if you're a CPA who would like CPD hours, hopefully you're here with us today, okay? Presenting with us today is Anish Verma, a quantum computing practitioner and research scientist who is currently working in a startup company. Very exciting stuff. We'll save some time for Q&A at the end, but feel free to comment in the chat as we go or raise your hands, and we'll try to keep our eye on that if you want to ask a question live. All right, with that, I will turn it over to you, Anish. Looking forward to it.
Right. So, thank you very much, Irene. It's an absolute honor to be here presenting to you all. One request that I have is if you'll allow, or the host can allow, screen sharing for me so I can put my slides up. Perfect. Thank you. Alrighty. And as well, while that's being done, thank you so much to everyone here attending. Super excited to start talking. Now, I'll be trying to motivate quantum computing from a high level, just given the variety of backgrounds first, and then I'll get into some of the more fun applications. Righty. So now with screen sharing, here we go. Now you'll forgive me. This presentation is a year old, but everything is still relevant today. I promise you. So with that, if you haven't had the chance to look into who I am, right, I'll give you some background as to why, I am qualified to talk about these things. So for about 3 years, I was a research scientist, specifically for quantum computing algorithms applied to finance, in addition to being a quantitative analyst at 1Qubit, which is a Vancouver-based startup/small company that is focused on applications of emerging technologies generally to difficult problems today. Now, as part of this, I also worked at a company or a group in BC called the Quantum Algorithms Institute, which is a wonderful organization that I wish we had more of across the country, that aims to really bring together industry as well as the academic researchers to try to get this technology in the hands of practitioners and just eager beavers today. And some of you who may have participated in the recent competition held by IMI, I have, or may be familiar with STEM Fellowship, my other past organization where I helped contribute to their data science program, which involved helping out with the planning and supplement of workshops and activities like you're in today. But with all that out of the way, all the boring stuff, I wanted to chat a little bit more about the type of ecosystem that QAI offers, but also more broadly what we can almost expect to see going forward. Right. As you can see, there are a lot of big names out here that you're probably familiar with, from Microsoft to IBM, as well as a bunch of universities that I'm sure all the students here are familiar with, just being in Canada. Now, there are starting to emerge a lot of organizations like these that aim to broker the quantum computing experts to nurture the people that are interested in quantum computing, whether they be at the high school age, the undergraduate age, or even late into their career as a practitioner. And I'm hoping that as the technologies develop, that we'll start to see way more of these things. And I wanted to now give you sort of an overview of the timeline that you can almost see quantum computing sort of emerge, right? And I think the best way to do this, other than just throwing jargon at you, I think looking at it from the lifetime of a company, right, and its investors really shows a light into the momentum of quantum computing and where it hopefully will continue to grow. So like my previous company, 1Qubit, right, they were founded in 2012, right? So that's 11 years ago now, right? It seems like so long ago, but not very long at all, right? And only a few years into it, right, a lot of these larger companies, and in particular CME Group, right, the world's largest futures exchange, they saw merit in exploring these technologies, right, early on in its infancy. And following that, these leaders, right, that wanted to sort of nurture its growth, saw that they could benefit from it in the long term if they stayed on top of it, as opposed to letting the competition beat them to it. Right. And we're seeing even more of this today and cross partnerships between competing companies, for example, like Microsoft and Amazon AWS. But all of that is to say is that there's a ton of activity right now, and even with your own backgrounds in finance, would probably or may benefit from taking a peek into it, especially with the mass amount of resources that exist today. Alrighty. Now with all that motivation out of the way, right, and history, we can start to talk about what quantum computing actually is, right? Because right now, quantum is very much a buzzword, and I think it gets misused quite often. So let's kind of approach what it is, in a short word, right? The punchline of it is that quantum computing is fantastical, but we need to be careful not to be confused between what actually is possible, right, with current hardware, what is possible with future hardware, and what is just nonsense that movies spit out. um, so with that, right, what is quantum computing? The takeaway that I want you all to have effectively, right, is that quantum computing, or quantum computers rather, are a new category of hardware, right, that fundamentally processes information in a completely different way than classical computers, right? And of course, we're trying to build these machines, this hardware, to be similar enough to classical computers, where we can build programs out of it and make more algorithmic use, right? But the reason that this category of hardware is so different than classical hardware is that it explicitly leverages the laws of quantum mechanics, right? So the very laws of physics are leveraged to our advantage, right? And I'll give some examples of this later on. But what this results in is that for a large, or pardon me, for quite a number of types of problems, right? High level sort of thinking here, it can provide a speed up or a reduction in the overall complexity of the calculation you're trying to do. Now, in terms of applications, right, I'm going to be talking about finance here today, but there are a ton of really, really interesting ones, right, that may be of interest to you. One really promising one is with material and drug discovery, right? So one really cool example that we like to use in the industry is that you know, in discovering and screening new potential, drugs to cure whatever disease or vaccine or what have you, right? We need to understand the physical properties of the molecule in question, right? Of the drug in question. Now, the problem is these calculations are super hard, right? And without exaggeration, if you want a 100% accurate simulation, uh, your computation may take on the order of several decades, right? Which is of course not feasible if you want to be screening a large number of these candidates, right? And how we get around that today and in the future will be exploring things like machine learning as well as quantum computing to help accelerate these calculations to be within a tractable sort of time, right? Something well within our lifetimes. Now, with that fun stuff out of the way, right? We can now start talking about why, the physical nature of these machines that allow them to be so efficient, so powerful, right? So in a classical computer, right, information and all of its manipulations relate to bits, right? Classical bits, which are basically just ones and zeros, right? There are two states that are accessible and that we operate with to create the machines that we have today, right? The laptop or that's in front of you, the phone in your pocket. And the goal with quantum computers is to basically supplement that, not replace it completely, because there are still areas where classical hardware is just, makes more sense to use. But we want to start using this hardware to tackle these problems that are just, impossible really with classical hardware. And we're able to do that because quantum computers make use of something called qubits, right? And qubits you can think of as a combination or superposition of these one and zero states simultaneously, right? So we go away from the binary and go towards more of a spectrum, right? So for example, instead of just having, my the state be zero, right? I can have it be 25% zero, and 75% won, which is a really fascinating thing to think about from a philosophical perspective. But we're not philosophers here, right? We're here to talk about the applications, and I want to get into that. But this is a fun fact that you could share with your peers or your students or friends. Okay, so yeah, in summary, brand new hardware, right? Fundamentally different because it leverages the laws of physics. And as things evolve, we want to see this hardware solve problems that just are not possible on classical hardware. Okay, and if that wasn't motivating enough, right, for the analysts and investors in the room, let's take a look at how investments and have been going, and as well how the general market has been shaping up over the last few years, right? So this report was from a couple of years ago, right? But they valued or pardon me, they valued the annual value by 2040 of the entire cloud computing industry, right, and the benefits that it will bring at about $850 billion dollars. And of course, that's it's a massive number, and analysts say that it's only 17 years away. As a practitioner, I feel like that number is a moving target, really. So if we're not all if we haven't solved all the world's problems by then, worry not. But one of the cool things about this analysis is that it gives like a lot of the more practical areas where quantum computing is relevant, right? So in the bottom here on the simulation side, you can see the chemistry and pharmacy applications that I gave, right? But another big sector is in the general category of optimization. And from your courses and from your work, I'm sure you're all aware that optimization is a super hard problem, especially as you scale up to more and more assets, right? But this has the potential to really, really better inform the way we make our trades, for example, or the way that we hedge against risk. Anyways, moving from that, right? Here's a fun little plot I like showing that shows the general increase in U.S. investments. Towards quantum computing in a general sense. And I really wish that this had updated numbers from 2023, because we're starting to see even more consistency and increase despite the current economic conditions. And the worldview is quite similar as well. Last year, Asia, there were a few countries in Asia that put together a significant portion of funding towards the research of quantum computing. So this is a worldwide collaborative effort. But now, right, I'm sure you're almost bored of hearing about this context, right? So now we can start to get to the pragmaticism of it, right? How do you actually access quantum computers, right? Is it possible that right now or in the future that you can have like a desktop, right, like a tower in your own living room or your own workstation at home, or is it something different? Is that not feasible now / in the future? And great question, right? And not only from our point of view, but also for the companies that want to make use of quantum computing, right? Maybe there's a transportation and logistics company, in 5 years' time that really wants to use quantum, but they have no idea how to go about doing it, right? And that's where the different players in the quantum computing ecosystem come in, right? So I framed this around 1 qubit, just because this is almost this is the type of company right now where things come together, right? So in this bottom section here, right? These are a lot of the direct hardware providers, right? So you have companies like IonQ, NTT, right, that are focusing on developing specific hardware, right? Specific quantum computers that are useful for their particular applications. I can't give specifics on Dow, the chemical company, but they are working on specified hardware for their chemical simulation problems. Now, that's great. We have hardware manufacturers that are doing fantastic work. You also have some interdisciplinary folk that are working on combining quantum computing with machine learning to make it more accessible in recent times. And they're doing some really cool stuff that I probably won't be talking about in this talk unless someone asks it as a question later on. And then finally, the quantum cloud. This is where people like you and I and companies and whomever else are going to be able to use and access quantum computers right now, as well as for the near and probably medium term. As right now, the hardware is extremely expensive to build and even to run locally. And this is for a number of reasons that I can touch on later. But what I want you to know is that, a provider like AWS, right? It'll give you options on different hardware, right, from their hardware partners, like IonQ I mentioned here, D-Wave, Rigetti, and the different types of hardware, right? That's up to you to decide on which is best for you, right? Um, Talking to some of the logistics of it, D-Wave focuses on a particular class of quantum computing called quantum annealing, right? These lend very specifically well to optimization problems, to a very particular class of optimization problems called quadratic unconstrained binary optimization, or QUBO, right? Uh, Now, while they're pretty good at that, they're quite garbage at everything else, right? The annealers are, and this is not a dig at D-Wave. This is more of a dig at this particular architecture. Um, they will not be a suitable replacement in a sense for classical computers because they just operate in a totally different way. But these ones on the left here, right, the Rigetti's machine, IonQs, and a bunch of others fall under a more, I shy away from the word universal, but they tend toward a more broad class of quantum computing called gate model quantum computing. And these are the ones that are more familiar to, for example, classical computer engineers, right? Because they make use of gate operations in a similar way that classical computers do so, right? Except instead of operating on bits, they're operating on qubits. And there's a whole lot of fun stuff there to chat about. But moving on, right? So now that you have the access points, right? Now that you know where to go, right? What does an example workflow of this look like, right? Like, it's great that I can use Rigetti's machine or IonQ's machine or D-Wave's machine, but like, how do I actually implement it into my own workflow to ensure that it's consistent, to ensure that I can debug, et cetera, et cetera. And to ensure that I can update it as things change. Well, a lot of these cloud providers, and in particular AWS and Microsoft for Azure, they have done a phenomenal job at taking from the software developer as well as the researcher perspective, right? They want to make the process as easy as possible. So on your end, right, you'll access from your laptop or from some other device, right, from the cloud console, and you'll be able to submit your job in the same way that you would to any cluster or similar to how you would access an API right now in Python, right? So the process on your end is super easy, right? You write up your code, you write up your problem, and then you say, hey, I want to use this endpoint from AWS, right? It submits the job, and then you get the results within some period of time. Now, the nice thing about having it built with a cloud provider like AWS is that they offer you genuine tools to help you debug, right? As well as they offer the compatibility and I guess compatibility is the right word here, the compatibility with other types of architecture or high performance compute that you may need. Like a really cool example that we've actually done at my current company, Good Chemistry, where we focus on AI and quantum for chemistry problems. Um, we've we were able to simulate a molecule in a way that leveraged both quantum computing and AI, and we were able to do it to chemical accuracy by leveraging both of these things in a record-breaking time. We have a publication about this coming up at some point in the future, so be on the lookout for that, just to show you the synergies that can come into play. Wonderful. Okay, so now in terms of applications, I wanted to focus on two fun ones, right? One that probably all of you have approached at some point in your life, whether it be in courses, your own work, etc., and that is portfolio optimization, right? The second one that I'm going to focus on, the second application, will be on a credit scoring problem, right? And this one will fall under the category of quantum machine learning. But the goal for us here is basically to demonstrate how this would be used, currently, as well as for general workflows in the future, right? Okay, wonderful. So with this, right, let's talk about a quick intro to portfolio optimization, right? I don't want to explain to the experts here because I'm out of my depth as a lowly physicist, right? But I do understand at the very least, right, that broadly speaking, portfolio optimization comes down to finding the right balance between for example, the return of your portfolio and the risk or the maximum drawdowns that you can encounter in your portfolio solution, right? Now, this is great, right? And there's a ton of work up there right now about how to best optimize like certain portfolios, what other factors to consider, et cetera, et cetera. But I'm sure, as we all know, this can become a very, very difficult computational problem, especially with the more assets you have and the more parameters you bring into the model, right? Generally speaking, it's a difficult optimization problem. But quantum computers have the effect or the benefit of speeding up this process. Now, there's a huge asterisk there that I don't want to overlook, and that asterisk, right, and that asterisk is that right now, because of how small the quantum computing hardware is, it will not offer you a practical speed up today in this state. However, the hardware is growing at an exponential rate, right? Like year over year, we're seeing much larger, pardon me, capacities of quantum hardware. I think a really fun example to look at is with IBM and what they've been doing over the span of just a few years, right? They went from on the order of tens of qubits to hundreds of qubits, and now they're getting really close to announcing their first 1,000 qubit chip, right? So the promise is there. We just need to wait for the hardware to catch up, and that promise is faster computations and the ability to address a larger number of assets for this problem than you would be able to with classical computers. So with this, right, I want to go over two really key algorithms that exist right now for gate model quantum computing. And those two algorithms are called VQE for the variational quantum eigensolver and QAOA with the quantum approximate optimization algorithm. Now, these are spooky names even for me, right? Like quantum approximate optimization. Now that's too much for me to say already. And QAOA is just a gross word to say in general, or a gross acronym to say. So with that, right, let's talk about the algorithm so you can at least remember what they're actually there for, as opposed to getting stuck on the names like I often do. So in this process, right, in this example that I'm going to show, and I will show some code later on, just depending on how we do with time, is that we know our optimization problem, right? We know that we want to balance between total portfolio returns and the risk, measured by variance, for example, in our portfolio. And what we'll need to do is take that high level problem, right, turn it into an optimization problem that lends well to the current paradigm of quantum computing, and then finally implement these two algorithms and see what the results look like, right? So, pretty easy, pretty simple. And, after this, you guys can have more familiarity with quantum computers and hopefully even try it out yourself through quantum software development toolkits like Qiskit, which is IBM's software, or maybe you want to go for some other fancy startup, your choice. Okay, so setting up the problem, right? I'm going to show you this equation because I think this is the easiest way to explain it, right? And if you're not super familiar with optimization problems in general, that's no problem to me. We're gonna go through it quickly right now. So here, right, we're defining the optimization problem through the following equation, right? We want to maximize or minimize, right, some objective function subject to some constraints, right? Just that's how we do optimization in a general sense. Okay. Now, we already said how we wanted to maximize the portfolio returns and then minimize the risks, right? And the best way to do this is having these opposing terms in a sense, right? These opposite sign terms. The term on the left here, this mu transpose x, this will be the term that talks about our portfolio returns, right? So the magnitude of return that we get over some period of time. The term on the right here, this will be this will be our risk term, for lack of a better word, right? So sigma here will be our covariance matrix, right? So how we understand the relationship between the returns of each asset. Q here is our risk appetite effectively, right? So if we set this term to 0 or some low number, right, that means I don't care at all about risk. That's for some risk analysts to look at it, right? I only care about returns. If I tune Q to be some massive number, right, then I'm terrified of losing all my money, right? So I want to hedge against that. Okay, so fairly easy, right? Fairly straightforward. And then the last thing that we really need to talk about, right, is the constraint that we put, right? And how we've defined this problem, right, is that we want to have the sum of all of our pardon me. We want the sum of our assets to meet some certain condition, right? And how I've arranged this problem is I've allowed our variable x here, which shows up everywhere, to be a 1 or a 0. And you may ask why. That sounds a little different. Well, we're turning this into an asset selection problem effectively, right? Where we incorporate the portfolio weights later on in the process. Now, to summarize, right, we have our objective function that we're going to use to find the best portfolio, and that best portfolio is found through the effectively optimal value of x, where each of these elements are either ones or zeros that tell you yes or no, you want this in your portfolio. Okay, so now we can get into the quantum algorithms and how to solve this problem using those algorithms. Also, quick reminder, if anyone has any questions throughout, put them in the chat and I'll do my best to get to them when I can. I realize that showing math and going through it can I can get too eager. I love math too much. So please stop me if anything is unclear. Excuse me. Okay, so the first algorithm that we're going to talk about is the variational quantum eigensolver, or VQE, right? And I want you to know one core element from physics, right? That will sort of motivate why this works, right? So this hybrid algorithm, it relies on something called the variational principle, or the variational method from quantum mechanics, right? And although these terms may look spooky or unfamiliar, right? We have some fun ways, or a very clear way of looking at this, right? So this first equation here, right? It's saying that that our state, so our state of being of a particular particle, right? Operated on by some operator h, and in this case, h is called a Hamiltonian. It corresponds to energy. It's equal to a scalar value, a number, right? So this is saying that for any given state of any given quantum system, right, the energy will be some number E, right? Now you'll notice that this psi and this E, they both have a subscript, a sub-zero to all of them. And this corresponds to something called the ground state of the system. And in physics, all this means is that the ground state of the system is the lowest energy state of that system, right? So if you think of it as like having a ball on the ground, right? We all know from high school physics that if you pick it up, it gains potential energy, and that would have a higher energy than it would on the ground. And it's a similar kind of principle for molecules and quantum systems, just with a different force, basically. Now, the really cool thing is that we are guaranteed by the variational principle, by the variational method in quantum mechanics, that if we use that same operator and act on any other state that corresponds to the system, right, or an excited state of the system, it will still give you an energy, a scalar value, but it will always, 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 always be greater than or equal to the ground state energy. The only way for it to be equal to the ground state energy is if the wave function, this psi thing here, the state, is equal to psi naught, right? So that's the first thing, right? And already, right, some of the really keen folk over here may be realizing that, wait a minute, this sounds like there's an optimal value for energies in the state of the system, right? And in a sense, that's true. So we can effectively take that problem, right? Map it to our equation, right? The optimization problem that we defined, and then use a quantum computer to simulate that and to spit out the answer that we will hopefully want, hopefully the right one. Okay, so wonderful. Now that we have that physics background, right? Let's talk a little bit more about the nuance of what it means in this algorithm, right? So in order to actually encode it, right, into the code, into the quantum computing hardware, we need to have something that we can vary, right, in our optimization problem. And lucky for us, there's a really easy way to do that, right? We can directly encode a wave function, right, or a state into the quantum hardware. We call this guess at the wave function, our guess at the optimal state, our guess at the optimal portfolio, the ansatz, right? And this ansatz will have some parameters that we optimize, in a classical sense, in order to end up with our final result. So once we have the ansatz put and some guess at a parameter, right, we incrementally change these parameters, optimize it, and then feed that into the next iteration until we reach convergence. And that's our optimal portfolio. So that's a high-level overview of the algorithm, right? If you prefer diagrams, this is probably a lot easier, right? So you prepare your ansatz, you compute the energy or the expectation value using the quantum circuit, and then you use a classical optimizer to find better parameters. As well, this step could also be made quantum, but there's a lot of work being done right now on how to do that, right? How to modify this hybrid algorithm and turn it into something that is purely quantum. Okay, awesome, great. I want to talk quickly about the ansatz, but I won't go into too much depth here because I feel like it's a bit out of scope for this talk. So our guess at the wave function, right? That defines, or that really dictates how fast, how quickly we're going to converge to a correct answer, as well as how quickly, or pardon me, as well as how accurate the overall result will be, right? And you can think of it you can think of it as just being as simple as that, right? If my function, when I plot it out, if it looks like the thing that I'm going after, that's great. It'll take like a couple steps. If it looks nothing like it, the optimization landscape will be kind of gross and a little bit more difficult for the algorithm to navigate. But in principle, right, it should get there eventually. One other consideration that's relevant right now is that the choice of your ansatz is really dictated by your hardware capabilities. And the reason I say that, or to elaborate here, you want your ansatz to be as nicely tunable, right, as well as close to the I guess the goal as you could possibly get. And what that means is that you're going to need a lot of operations or gates, right? That's what these things are called, operations on the qubits in order to arrive at that. But if we're limited by the number of qubits, right, that forces you to have a smaller problem, right? So with that, I'm going to show a toy example of this algorithm that makes use of just 3 qubits, three assets, right? But it'll show you the type of workflow that you can expect as things grow. Okay, so wonderful. So that was VQE, the variational quantum eigensolver, and now we're going to talk about its sister algorithm, the quantum approximate optimization algorithm. And this belongs to the same family of quantum optimization algorithms, but there is one key difference. I'm just going to flash this slide at you, and then we're going to move on because it'll require me to give a much more in-depth lecture of quantum physics. But all you need to know is that the ansatz is more sophisticatedly, if that's a word, chosen, right? So instead of just having these certain operations, right, we have a very, very specific guess at the wave function that in fact is informed by the optimization problem right from the get-go, right? So the difference here is that we are going to be informing the guess at the wave function right from the get-go by use of this functional form here. The H's in here, right? These capital H's, these correspond to, or they will correspond to the optimization problem, right? With our mu, our q, and our sigma, right from the get-go, as opposed to just having some gross guess that looks like this. Okay, so with that, right, we can now start to see it implemented. Just checking the time here quickly. Okay, so I'll show the code at the end if anyone has a question and we want to see it implemented. But with that, I'll skip straight to the results. Okay, So first, tell you about the problem. The problem is that I had three assets, right? That I was too lazy to calculate in a classical way, right? I have three assets, let's say Tesla, Microsoft, Amazon, right? And from that, right, I wanted to pick the best two out of those three assets that will give me, the optimal portfolio, right? Um, in my case, I opted for looking for the highest return as opposed to the smallest variance, right? And the output that I wanted would be, this selected subset or sub portfolio. Okay. Now, in order to run these algorithms, right, I input all the data I needed to based on the algorithm architecture that we defined, and it output the following two graphs, right, up top over here. On the left, we have the results from the VQE, and on the right, we have the results from the QAOA, right? And this probably looks completely foreign to a lot of you, right? Because in a classical optimization problem, we have one very, very clear answer, right? There's one answer, and then nothing else gets consideration. But because we're working with a quantum system, we have to understand that we're dealing with probabilities, and we need to understand how to analyze these probabilities, right? Now, on the x-axis here, or sorry, on the y-axis here for both of these plots, you'll see the relative probability or probability density, pardon me, probability of each of the possible portfolios, right? And the probability means the probability of it being the best one, effectively. On the x-axis here, we always have these three digits, right? In this case, it's 000. Second case, it's 010, and so on. The zero means that I did not pick in this case, the nth asset. So in this example, this is a portfolio where I chose none of the assets. I have an empty portfolio and my money does nothing. In this far right example, right, I said screw it and I put all my money equally into all three of those assets, right? But if you recall, the constraint that I just said is that I only want two out of three assets chosen, right? Not three, not zero, not one, not or yes, two. And we have some probabilities for the nonsense portfolios, but in VQE there is a very clear winner where I have the first asset selected and the last asset selected in my two out of three portfolio. Now on the right side we have the results from QAOA, and we have a far messier distribution of probabilities, right? But if you'll recall, we informed our problem by our optimization problem, and that included the constraint that we put into it, right? And that constraint was we have to select two out of three assets. And now we can see, right, that the three best probabilities are the only ones that match that constraint, right? 011, 101, 110. So we not only do we get what the algorithm say is the best portfolio, we also get more information into the problem itself, right? And in principle, we have more to work with in deciding how we want to do this as well, right? These calculations can be run very quickly, especially with this small size. So this can be done on a rolling basis, right? If you're a portfolio manager, right, maybe you want to do this on some regular recurring basis and use that as an input into into how you make your decisions. Now, that's great, right? I showed you probabilities and I said that this one's the best portfolio, but how do I know 101 is actually the best portfolio? Well, I map it back to our problem, right? And I just plot the total portfolio value, right? And in this case, the 101 portfolio, right? It's the very clear winner by a long shot, right? Although you'll notice, right, just based on how I defined the question, there's this massive drawdown right here, right? And you can't see it in this plot, but if you update these plots, I'm sure there'd be a similar decline, especially in recent times. But again, right, this is something for the analyst or the experimenter to work with. So neat stuff there. Okay, so that is this small example of portfolio optimization, and also show some updated results if prompted at the end. But I want to talk to another application that may seem more relevant for people that want to go into different areas of finance, or just want to see how else this technology can be used, right? Excuse me, I had to clear my throat there. So now we're going to be focusing on the application of quantum computing to credit scoring, a credit scoring problem. Okay, so with that, right, we need to know a couple things, right? A couple contextual things. Um, once again, I'm a physicist by training, so don't grill me too hard on the motivation for credit scoring. Um, but I will say that this is a pretty difficult problem, right? Maybe significant is not the right word. Um, in credit scoring, right? In computational finance, basically, how do you figure out what are the right categories or data types that you want to input into a credit scoring model, right? Now, sure, this probably won't be of particular interest to an individual like myself, right? Or any one person, but to a larger group, right? They may want to incorporate this technology to improve what they have and their ability to rate a company, for example, right? Alrighty. And one of the important things that we, I guess, discovered in talking to some of our partners, at my time at One Qubit, is that people care, or these companies care more about the flexibility of the solution, right? And how easily it can integrate into their existing software or technologies that they use to do this credit scoring. And lucky for us, quantum computing in principle can offer a speed up, first of all, but second of all, this sort of ease of integration, as opposed to other solutions that would require you to completely rewrite the architecture of the solution. And we can do it using actually either category of either paradigm of quantum computing, whether it be annealers or gate model quantum computing, which is pretty cool. More options is always a good thing. Okay, so just to emphasize the fact that credit scoring is a very or feature selection in credit scoring is a very hard problem. We need to understand that not all features are really relevant, right, when deciding what a good or bad credit score are, right? Or rather, they don't have the same weight as other features or factors may. But on the and by this virtue, right, if we can eliminate those redundant features, right, reducing these number of features, we can probably improve the model runtime in addition to its accuracy. But there is a flip side to that, right? We have to be realistic, right? People lie, or maybe there's going to be a particular, economic or financial condition where those factors are way more relevant than they are at another time, right? Maybe this misleading data from people lying, right? Maybe those redundant features might actually be a super corroborative feature in defining a proper picture of the company or the person. Okay, and with this in mind, we want to balance between the influential as well as the independentness of the features that we choose. Okay, so with that sort of high level thing, right? Now we need to think about like how many true possibilities there are for some number of assets and features to be selected, right? The example that we did and we wrote a white paper as well as a textbook chapter on was for, this is back in 2016, was for 48 total features where we wanted to select some smaller number of them. And for 48 features, there's more than 280 trillion possibilities. So it's a lot. It's not ideal to go through those one by one or even just run it in a classical optimization scheme, right? So what we can do, what can we do? We can do a couple things, right? Purely classically, we can just rely on machine learning, right? And just hope that the computer doesn't break, right? Or we can try to make use of a combination of both machine learning, right, as well as quantum computing to basically speed up the optimization part of it, right? Feeding into this machine learning, categorization algorithm, and then getting the best subset of features, right? Okay, great. So now, once again, we have to cast the problem in an appropriate way, right? Similar to how for purple optimization, we had that objective function. We want to do something similar. So now we want our model to take in both numerical data as well as categorical data, right? These features, right? For example, they may be just some integer, right? They may be, like the number of years that like a person has in education-wise, et cetera, et cetera. Or, like I said, it may be categorical. It might be, just the country where the thing of interest exists, right? And in some cases, we might have missing data, right? And the fact that that data is missing may be informative in itself, right? Et cetera, et cetera. So all these different data types we want to incorporate because we feel that they are going to be relevant to an accurate credit observation, right? All right. Okay. So with that, talking a little bit about the matrix mechanics behind this, right? We can construct, some matrix, we'll call it U in this case, where each of the columns represents a feature, and then each row represents the specific data values, right? So this is the same thing as a spreadsheet. We just turn it into a matrix to be usable for this application, and in a pretty easy way too, right? And then the goal in principle would be to find the vector, right? That informs us on the credit worthiness of the particular individual company, et cetera. And here we're going to take a similar approach where the elements of this v vector will be 1 or 0, right? Where in this case 0 represents the acceptance, right, of this feature, and 1 represents the rejection of that feature. Okay, so now that we have this, this problem set up, right, we can start talking about how to actually use it, the results, and so on. Okay. Oh yes, I should probably show the thing that we're optimizing. Okay. Uh, so the objective function that we're going to be exploring is as follows, and this is more complicated than the original one, but if we break it down, it truly is as simple as what we had before, right? So on the left term here, right? This will be talking about the influence of the feature, right? How influent that one particular feature is, whereas this other one over here, right, we'll be talking about the independence effectively of that feature, right? Whether or not it is a redundant feature. And we're going to be minimizing this instead of maximizing with the other problem. But hey, that that's just one of these problems that we've been talking about, right? The QBOs, the quadratic unconstrained binary optimization problems. So with that, we can run it on either a quantum annealer or a gate model quantum computer and try to get some meaningful results. So let's just take a look back at the problem itself, right? It was hard because we have the issue of there being so many different possibilities, right? And we want to understand how how things may behave, right? Not for the sake of the algorithm, but just for the sake of us understanding like what the heck we're doing, what a good measure of success is, and so on. So let's just randomly sample, right? Let's say 10,000 subsets of these features and so on, and just seeing if we can identify, from from guessing basically the best detected subset and what information we can draw from that. So in this case, right, we drew 10,000 random points, which when calculated explored 432,354 feature subsets. Great. And then we took the mean accuracies for each group of those 10,000 subsets, right, and plotted them here. And the information that we extract out of this to help evaluate our model, right, is that we can see well, from this plot we can see various um, peaks or trends in this curve here, right? And we identified that, out of this random sampling, the best accuracy for this for just a machine learning model, right? Just picking and randomly choosing, right? The best accuracy that you can probably get is about 76% or so, right? And that's just seen here, just left to right here. So about 76% with the following error, right? And our goal, right? We probably want to get it less than the total number of features if we're doing a feature selection problem. And we settle on 35 or less here. Just we want to demonstrate the process of improving this. Okay, so with those success criteria is defined, let's see how this actually works. Okay, alrighty, fantastic. So how we combined machine learning and quantum here, right, is we basically took a classifier, right? Just a simple logistic regression classifier and combined that with our quantum or our QUBO feature selection, right? So in principle, the feature selector, right, and the classifier, right, the logistic regression classifier, they were placed together on the interior of the loops, right, so on each side, and then that process was optimized until we ended up with the best set of parameters, effectively, or the best set of features. Pardon me. Okay, and here, lucky for us, in terms of ease of implementation, we only have a single optimization parameter as opposed to, a hecton that you may find in a classical machine learning application. Okay, and that also, just as a reminder, that meets our earlier criteria of having this being easily implementable, for some larger company. Okay, so with that, let's actually see how things perform, right? So on the bottom here is our alpha parameter, right? That optimization parameter, and it shows, in principle, as alpha goes lower, the independence, right? The relevance of independent features, whereas on the right, it's biased more towards the more influential parameters, taking complete disregard on whether or not they are redundant. Okay. And we see a couple really cool things, right? So the first is almost expected, right? So the cardinality of the problem, it blows up as you take more and more features in effectively, right? As you put greater emphasis on the influence part of this algorithm, right? Um, Now you also see that this accuracy, right? Just depending on how this problem is done, in these computations, that it ranges between 70% and what is it, 76, 77%, give take, right? So our initial analysis of the range, right? It's spot on so far, right? Now we just had to figure out like what the actual optimal solution is here. Okay. And in order to do this, right, all we need to do is zoom into this region here where we actually see a peak of accuracy, right? And then see what feature set that corresponds to, right? And in doing that, we're able to get, at this influence parameter of 0.977, um, an accuracy, an accuracy of, I forget the exact number, but if you look right, about 76, 77%, right? But with half of the parameters that were initially defined. So we took this feature set of 48 parameters and halved it down to 24, right? Through this paradigm, which is pretty cool, right? Not only do we meet the success criteria of the accuracy, right? That was possible from our analysis of that random sampling, but we also have the features, um, far beating our goal of getting it below 36 features. So that's awesome. That's great. I did that with just quantum and classical machine learning. But how does this actually compare to other methods, right? Like is it useful in terms of accuracy, right? Is it useful in terms of reducing the number of features? Well, to address both of those specifically in terms of accuracy, right? Just compared with other simple ML algorithms, right? A recursive one and random max search, we get pretty comparable accuracies when looking at the errors, right? So at the very least, right, with this study that was done in, I think, 2016, 2017, with those early machines, we were able to meet the accuracy compared to, these stronger or solid benchmark machine learning methods. But the cool thing at the time was the fact that out of all of these methods, we were able to rapidly reduce the number of features much more so than the other methods, which is a pretty neat result in itself. And now that the hardware has grown quite significantly in the span of what, 6-7 years, um, we've been able to see a greater resilience and robustness of this algorithm, which I think is fascinating. Um, with that, right, we've delivered the punchline, right? We've answered what quantum computing is, right? We've understood the ecosystem, its context. We haven't seen it implemented in Python because I chose to skip over that, but it's easy, I promise you. And finally, right, we have two near-term applications that can be played around with right now that can almost motivate you as practitioners, students, what have you, to explore quantum in your own workflows and see how it can, potentially help you or your research or your work in the future. But yeah, with that, right, I believe we have time for questions, so I'll stop sharing and I'll allow the floor to speak.
Okay, thanks, Anish. That was great. And I like the way that you described it as a different category of hardware. And also like the way you talk, that actually leverages the quantum physics principles, which I guess you need to know a little bit about if you're going to use them. And also the way that you can use that, really, it's a speed thing. And it's also, I like that, the flexibility, like if you can actually incorporate that into your system. So that's pretty cool. We have a question. So let's ask Ulrich.
Hi. Yeah, very, very interesting talk. I'm a fan of quantum computing myself. So we started exploring it for chemistry. So if you do have a preprint, I know your paper isn't published yet, but if you have a preprint you can share, let me know. And in our experience also, accuracy is really, really good for VQE. And but where we see a problem, and I'm very interested what you find, is time is absolutely not competitive. So essentially, once we have a universal quantum computer, there will be algorithms that will be exponentially faster. But VQE, because we have to do so many quantum measurements to get actually the expectation value, will be inferior to the classical algorithms. It's fantastic that it works and that we can play with it, but it seems to be inferior in terms of time. And we would obviously, we want a quantum advantage. We want it to be superior. So what's your feel? Do we have to wait for a universal quantum computer, or will these variational approaches like VQE somehow catch up?
Yeah, no, I think so. First, thank you for the comments and question. I think you're 100% spot on there. In terms of for finance in particular, right? I totally agree with you that in terms of time complexity, right? VQE probably isn't the way to go, right? For portfolio optimization, especially. But I do think that, or not even think, there is active research being done right now to explore different categories or different families of algorithms that would lend better to near-term hardware, right? So NISQ hardware effectively, that in principle can offer a speed up. But realistically, like you probably are well aware, the fact that we have such noisy hardware, right, is really the prohibitive factor. And my personal feeling is that we won't see that quantum advantage, that speed up, probably until we start to reach the end of the NISQ era, right, the noisy hardware era, which is unfortunate. But I think in the meantime, developing algorithms that can actually work right now as a proof of concept is very crucial. Also, Ulrich, you mentioned that you're working on chemistry, so I think you'll probably find a lot more speed ups than finance will in coming years.
Yeah, no, there's a method called quantum phase estimation, which will run on the universal quantum computer, and that will be very, very fast. And we're watching carefully what's happening in the meantime, and we're playing with VQE. Yeah, thank you for your answer.
No problem. In the chat, I'm also gonna, just to advertise my own company relevant to you. If you want to talk more about, I guess, applications of quantum algorithms to chemistry problems in particular, I want to direct you to the following. I'll put it in the chat. But while I look for that, I see that there's another question in the comments from Ernest. Could you refer us to a source for Python implementation, ideally with examples more complicated than a hello world? Yeah, that's a really, really solid question. There are a couple resources. One, the quantum computing community in an applied sense is very supportive of each other, and I would point you to look at some of the larger I guess players, right, or research players. So for example, IBM, right, their quantum software development kit is probably the gold standard. If you're used to Python, it's effectively just a big old library, a big old package that allows you to simulate as well as access hardware. So I'll type that in the chat here. IBM Qiskit. And one of the nice things is that they have, their own textbook as well as their own GitHub repository, open source, in which you can see a lot more of these examples. They also host hackathons quite regularly where they have different application areas. Most recently, I think it was quantum chemistry, but in the past, they've also done things like finance. Another example is it's a company called Xanadu. They're based out of Toronto, actually, and their software is called Penny Lane, like the Beatles, like Strawberry Fields and Penny Lane. Okay, wonderful. So that was that question. Next question is from Atusa Asadi. Please forgive me if I mispronounced your name. Given the high variability of Cubo algorithm in the last slide, with respect to the classical techniques and similar performance, you could comment on the advantages of Cubo. Yeah, okay. This is a really good question, and similar to what Ulrich chatted about. So, in terms of the high variance, I guess, in these techniques, right? I think that's a a very valid concern, but in practice, how a practitioner would approach that effectively is they would just improve the function they're trying to optimize, right? The example that we gave was very simple, right? We split it up into two parts, just two effective terms, right? That only input where the input came from the selected feed from the universe of features itself. But maybe you as an analyst, or maybe the analyst that's using this algorithm, right, can fine tune that based on supplementary data sets or what they know, right? Similarly to machine learning in general, right? The better your data, the better your results. I don't like leaning on that as a crutch, but I think from a pragmatic point of view, a practitioner's point of view, that's how you would approach it. In terms of performance, right, this goes back to what Ulrich was saying and my answer there, in that right now with the current noisy hardware, right, and the algorithm types that exist right now, in terms of performance, if I got on a supercomputer right now and just did something else, probably be way faster than quantum right now. But again, I'm an optimist because I'm in the field, so I like to think that the hardware will catch up and accelerate quite quickly.
So Anish, while we're waiting, maybe we have a couple of other questions coming, but you mentioned, I guess quantum computing is expensive, but you can use a cloud provider, like Amazon, for instance. Do you have any sense of how many people might be availing themselves of those kinds of services? And I don't like to put you on the spot there, but say in terms of Microsoft or Amazon, how much of their cloud services would you say might be in this area?
Uh, yeah. I think I can give some insight into that. So in terms of cloud providers, right, you have two main ones effectively, right? You have Microsoft and you have Amazon AWS. For AWS, their platform I think is called Bracket, Braket. And then for Microsoft, well, it's Azure Quantum.
Mhm.
So, but you also have these independent hardware providers, right? So like IonQ, for example, right? Or Honeywell, sorry, Quantinuum, they've changed their name, where they offer their hardware through these cloud providers, through Microsoft and Amazon, but they also have their own cloud provider that will get you access to their latest hardware, right? So for example, right, on AWS, maybe you have access to this is a made up number for IonQ, but let's say like 50 qubits, right? But if you go to them directly and use their cloud service, or sorry, their API, right? Then you'll probably have access to their latest hardware, which is on the order of hundreds, for example. So that's generally the considerations that a person or a company would need to consider before choosing a provider. And the other thing is that if you're a company or a person looking to do research in this area, right, or just use a solution, the individual providers, right, reaching out directly to the company, they'll probably work with you in a far more direct sense than they would otherwise. And honestly, that may be for your benefit. Whereas a Microsoft or Amazon, they probably won't be able to lend you the same level of support unless you have like a big research contract with them, which may be infeasible, right, compared to a smaller startup.
So still talking about lots of money and
Oh
lots of
yeah.
involvement. Yeah, and lots of expertise. Yeah.
Yeah. Well,
Okay, we have another question there by Atusa.
is there a possibility of sharing the code for the examples? Yeah, yeah, actually. So with the portfolio optimization one, there are a couple different resources that I can point you towards, and I'll do that in the chat just after. But for the credit scoring problem, I don't think that's a public repository. So that was done like at our time at 1QBit, And at the time, it was a private repository. But there is a textbook chapter, or if you just go to OneQubit's website and look at their white papers, you can see, things clearly defined, and there are links to certain code examples. So I'll try to find you those links right now, actually.
Okay, in the meantime, while Anish is looking, anybody else have any questions, maybe even of a more general nature? As I mentioned, I think for many practitioners, it's at a point where not quite there yet, because you're putting a lot of trust in the quantum computer. Also, you need a fair bit of knowledge. I think, Anish, your knowledge is quite exceptional there. Just sort of at least figure out what your problem is and what you're going to do there. And forget all the other issues of the machine learning piece, for instance, and the kind of information you're training your algorithm on. Although it's moving very quickly, it still got quite a ways to go, I would say.
Absolutely. Yeah. So I also see a question from Brian here. Can qubits be on and off at the same time, or do they have to be partially on and off? Okay. I'm trying to find the best way to answer this. So yes to both of those questions in a sense. So when you have a qubit by itself, right? It's a quantum system, right? That before a measurement, right? Before collapsing the wave function, it is in a superposition of in this case, the 1 and the 0 state, right? The on and the off, the spin up and spin down. Now, that wave function is collapsed, and then a particular solution is like one solution out of all the possibilities is obtained, right? So before measurement, the system is in a superposition of all those states. So the qubit is on and off at the same time, blah blah blah, with different probability density weights. But then once you actually make the measurement and use that to inform your final result, that gives you a single answer. The reason that you saw a probability distribution in that plot that I showed is because that was the result of multiple measurements, right? And because the quantum system is probabilistic, you're gonna have to run this multiple times until you're able to build out that distribution and then get the clear cut, for example, answer. I hope that answers your question, but if not, I can add some clarity there.
Okay, thanks, Anish. Michael, any questions that you might have?
No, I just wanted to thank you, Anish. I'm a little bit out of my element here, to be honest, but your presentation was great and I really enjoyed it.
Yeah, absolutely. Awesome. Any other questions from anybody else? Feel free to reach out to Anish. I guess separately, Anish, you've given your company there in the chat if they want to reach out. But yeah, if there's no other questions, a great session. I learned quite a bit. And again, like Michael, I'm a little bit out of my depth, but we know this is coming and it's moving very quickly. So it's great to have you here to explain some of the fundamentals there. So thank you very much. And thanks everybody for joining in, and we'll see you all the next one. All right. Thank you. Bye-bye.
Thank you, everyone. Bye-bye.
Thanks, Anish.